Okay, now the question asks us to find Taylor series expansions for the following three functions. And they want the expansion at a given point x0, and they only want the Taylor expansion up to the second order, and they keep all the higher orders, just neglected them. Okay, so here are the three functions, and I'm just going to do the first one, and you'll see the idea. You can know, you will be able to know how to do this last two. Okay, so this is the first function. Okay, and to do the Taylor series expansion up to the second order, we know the formula is that the f of x will be taking expansion at the point x0, and that's the zeroth order term. This is the first order term. This is the second order term. And these are all the higher order terms. Remember that this is a row vector. So you have a row vector here and a column vector here. That gives us a scalar. And this is a row vector, and in the middle that's a Hessian matrix. And x minus x0 is a column vector by default. So this also gives us a scalar. So now what we need to do is just to figure out what is gradient and what is Hessian is. So for this function f, the gradient is just to take the gradient partial derivatives with respect to x1 and x2. So the partial derivative with respect to x1, you can see that only the first term involves x1. So we take the derivative with respect to x1, we'll get that. And when we take the derivative with respect to x2, we'll get this. Okay, and then we can get the Hessian, which is just a collection of the second order derivatives, and that gives us this. Okay, so the first row is the partial derivative of this term with respect to x1 and then x2. So that is these two terms. There are these two terms. And similarly, the partial derivative of this with respect to x1 and x2 will give us these two terms. Okay, remember that the Hessian matrix is symmetric if the function is continuously differentiable. Okay, so that's also what you can see here. They are the same. Now we just need to plug in the values because f of at the point 1, 0, we want to evaluate the function f at that point x0, which is 1, 0, and we'll get the 2. Just plug in 1, 0 here, 0 here. So we can easily see that this is 2. Similarly, we'll plug in the values of 1, 0 into the gradient Hessian, we'll get this 2. Okay, and then just use this formula here and plug in the value here. We now know this, we also know this, we also know the x0, which is just 1, 0, and also know the Hessian. So we just plug in those values. So we have all this, all this thing here, and plus this term. Okay, I will throw out this term, but as I asked about the question, but there should be some higher order terms if you want to get equality. Okay, otherwise it will be just an approximation. Okay, so now you just simplify the formula and you get a function of x1, x2. Okay, remember that this is a quadratic function of x1, x2 because you expand this Taylor expansion, so that is a polynomial up to the second degree, or degree 2. Okay, so that's why you get a scalar in the end.